and welcome back to CS 11747 Neural Networks for NLP. This is Graham Neubig, and this time I'll be talking about document level models. So we've talked about a number of NLP tasks throughout this class, such as language modeling that tries to predict the probability of sentences, parsing that tried to predict syntactic structure, classification, which tried to predict labels, and entity tagging, which tried to predict particular spans belonging to a particular entity. And we can make connections to tasks over documents or longer sequences as well, such as document level language modeling, where we predict the language on the multi-sentence level, document classification, predicting traits of entire documents, entity coreference, so which entities correspond to each other in contrast to NER, and discourse parsing, how do segments of a document correspond to each other, which is similar to maybe phrase structure semantic parsing. So these are predictions using documents or prediction of document structure, and I'm going to be talking a little bit about each of these tasks. So the first one I'd like to talk about is document level language modeling. And so basically we want to predict the probability of words in an entire document. And obviously, sentences in a document don't exist in a vacuum. You're likely to be talking about similar things in the next sentence as you were in the previous sentence, and we want to take advantage of this fact. So if we think about one of our modeling methods that we have, we can think about recurrent neural networks, or more generally autoregressive models that condition on the previous state. And recurrent neural networks in particular pass information from the previous state to the next state through a hidden vector. And a simple way to expand these to document level is to simply continue passing the state from sentence to sentence. So one issue with this is that if your documents become too long and your memory is not large enough, you will have issues. But if you remember from when we talked about recurrent neural networks way long ago at the beginning of the class, there are methods to address this, such as backpropagation through time, or truncated backpropagation through time, where we just maintain the previous state here and don't backprop into the previous sentences. So there are ways to handle this in the context of recurrent neural networks. So theoretically, recurrent neural networks should be able to pass information in infinitely long number of steps. But one issue is that these models are not entirely learnable, or they cannot necessarily learn to do this well from whatever information we have, especially because if you remember, recurrent neural networks have issues with vanishing gradients over many, many time steps. So another thing that you can do is you can have separate encoding for coarse-grained document context. So you have a RNN for local and global context tends to miss out on the global context. And other attempts can kind of incorporate global context explicitly. So this might include something like a sum of all of the word embeddings in the document up until this point, or some other way of concisely incorporating document context. So now, of course, in 2021, everything is about self-attention and transformer models. And transformer models are also attractive because, if you remember, unlike recurrent neural networks, they pass information directly from word to word, so they might be a little bit less susceptible to the kind of vanishing gradients that you would get over long time steps. So one simple way to apply transformers to longer documents is to simply self-attend to all previous words in the document. And this is a relatively simple way to use document level context. And work such as Vojta et al. 2018 have shown that this actually does learn interesting correspondences. So for example, there was a time when I would have lost my heart to a face like yours, and you no doubt would have broken it. And you can see the it here, one of the attention heads is attending to heart, the antecedent. So you can see that it's essentially learning to do coreference, which we'll be talking about later. However, a major issue with these models is that computation of these attention matrices is quadratic in the sentence length. So if we have a sequence length, so if we have a really long document of, 10,000 words or something like this, then that would result in a 10,000 by 10,000 or 100 million size attention matrix, and calculating that would be very ponderous. So there have been quite a few methods that propose how to solve this issue. One is Transformer XL, and Transformer XL is basically doing something like truncated backpropagation through time, like we did with RNN models, together with the transformer. So the basic idea is we attend to fixed vectors from the previous sentence. And so if we look at how the standard transformer works, basically we would process one segment at a time. We would do self-attention. Let's say we're doing a left to right transformer language model, then each word would attend to all of the previous words in the sentence. However, when we reach a segment boundary, we basically would stop attention there and not attend back any further. So because of this, obviously that limits the amount of context that we can use to calculate the next word. And what Transformer XL does instead is, instead of drawing a hard segment boundary between each segment, it allows the transformer model, or it allows the transformer for the current segment to attend to all of the vectors from the previous segment. It just fixes them and doesn't do backpropagation through them. So because of this, this allows the new segment to reference information from the previous segment. And in fact, this is a really powerful method, because when the current segment attends to the previous segment, remember that the previous segment has also attended to the previous, the further previous segment. So this allows you to reach very far back in time to calculate the vectors at a minimal increase in cost. So this has also been expanded to something that actually does explicit compression over the previous steps. So this is something called the compressive transformer. And so essentially we have the current sequence here, and then we have the memory, which the memory is essentially transformer XL style vectors for each word in the previous few sequences. And then after we have calculated the previous, the value for the next sequence, there's a compression step that basically takes a certain number of the vectors in the memory and compresses them into compressed memory, which can also be attended over. So this is kind of like striding, which we have talked about before. It essentially compresses multiple vectors into a single vector to reduce our sequence length, and this allows us to attend essentially over a much longer sequence than the standard Transformer XL would be able to do. So switching gears a little bit, there are also methods for sparse transformers. And these are also essentially striding methods, but they're calculated over entire sequences. So the way it works is essentially you, instead of calculating the probabilities according to the full transformer, where you calculate the attention weights over every pair of sequences, they essentially calculate the attention weights over pairs of sequences for the recent values, and then they have a relatively large stride over the previous values after you get past your kind of local window here. And so what that allows you to do is it allows you to essentially do something similar to what was being done for Transformer XL, except instead of attending over the immediately previous segment, you're attending over something that looks a little bit more like the compressed memory here. And This also can be done at training time if you would like, because the strides reduce the quadratic complexity by quite a lot. So this is a good method to essentially use longer context at training time that's relatively simple. One issue with this, though, of course, is that the strides will reduce the number of things that you can directly attend to. So, for example, if there's one really important word like an antecedent in the previous sentence that you would like to attend to, you might miss it just because you're striding and not necessarily attending directly to that particular antecedent. So another method that people have used are adaptive span transformers. And the idea behind the adaptive span transformer essentially is that it doesn't necessarily attend directly to the entire context, but it can adjust the amount of context that it attends to. So in contrast to the standard transformer that has, a fixed amount of context that you might attend to when doing any particular word, this allows you to extend the context beyond that fixed value there. So this is kind of an interesting graph from this paper, which basically shows for each layer of the transformer model that they trained, how far back in history some of the attention heads chose to attend. And you can see that at the very beginning, at the very first few layers, basically it's attending to the minimum number of contexts, like 32. But as you get farther in the layers, the model chooses to attend a bit farther back, kind of indicating that once the model gets further on in the computation, it's realizing that referencing back to more information than just the current segment allows you to do better. So these can be combined together. The ideas of sparsity and adaptivity can be combined together. So if we look at the sparse transformer, basically it has a local context window and then kind of strides back into the past. The adaptive span transformer has essentially different size spans for each attention head. And these different size spans are essentially fixed for each of the heads, or at least they're over the immediate past. And what the adaptively sparse transformer does is it essentially attends back in the past, but it can choose which parts to attend to. So it may attend to this word, but not to intervening words and other words like this. So this is good because, if there's a really important word like an antecedent, you can attend directly to it as opposed to having to attend to it through, striding or some other mechanism like this. But the disadvantage is that it becomes more difficult essentially to use a particular context window or to make computation effective by limiting yourself to a particular context window. So this kind of gives rise to a chicken and egg problem in sparse attention. So we can sparsify relatively low scoring values to improve efficiency. Anything that is not included in our sparse attention. So basically, anything that has an attention weight of 0, we can not do any computation for at all. However, if we want to do this with respect to relatively low scoring values, then we need to know which ones are relatively low scoring. And in order to do this, we need to calculate the full attention matrix. Or, doing it in a naive way, we would have to do so. So because of this, this means that it's non-trivial to achieve both adaptive sparsity and the efficiency gains that you can get from sparse transformers. So a kind of clever way to handle this is called the reformer. And it basically allows for efficient calculation of sparse attention by basically combining together a number of tricks. And the first one, clever engineering, methods that allow you to do this. So the first one is that if you remember back to how the transformer is implemented, we have key vectors, query vectors, and value vectors that are calculated in the attention. And the first thing that the reformer does is it shares the key and query parameters to make sure that the keys and the queries end up essentially in the same space. After it does this, it uses a method called locality-sensitive hashing, which I believe I've talked about in an earlier class, which allows you to efficiently look up similar vectors. And just to recap, the way it does this is it does this by essentially turning vectors into hash functions by using a method of random projections. So then you get a hash value, and then after you've gotten the hash value, that allows you to turn individual examples into buckets. So we start with the sequence of queries and keys, and then we do LSH bucketing to convert these queries and keys into buckets. So we have a blue bucket, a yellow bucket, a white bucket, and a magenta bucket over here. And then after we've done this, now we just calculate attention among things that are basically in the same bucket. And because we do this, now we no longer need to calculate over every pair, but can just do among the blue ones, among the yellow ones, among the purple ones. However, the issue here is that this is not necessarily easy to implement on GPUs, for example, because the number of examples in each bucket may be different. So they also have some clever tricks to chunk things together and perform attention among things that are in the same chunk. So this is you can look for more details in the paper if you'd like to learn more about this. But long story short, the reformer is essentially a way to efficiently do sparse attention. Another method that people have looked at in order to do these kind of longer document transformers is low rank approximations. And so calculating the attention matrix is expensive, so is there a way to approximate it by using a lower rank matrix? And there's a couple methods that do this, but both of them, what they boil down to is you have the softmax matrix that you would like to calculate. And so instead, you calculate it with a kind of tall matrix multiplied by a square matrix multiplied by a wide matrix. And each of these matrix multiplications is a lot less expensive than expanding the full matrix here. So the linformer is a method that adds low rank linear projections into the model to achieve this kind of low rank this low rankedness. And the Nystrom former approximates using the Nystrom method, sampling landmark points. But long story short, both of these are essentially a way to create a low rank approximation to the real softmax matrix. So now that I've talked a number of ways that you can build these kind of document level models, specifically with self-attentional models, how to evaluate them. So the simple way to evaluate them is using perplexity or classification over long documents. I think these are perfectly reasonable ways to calculate long document models, especially they've been used for character level perplexity metrics, for example. And if you calculate on the character level, then every document becomes quite long because there's many characters, at least in English. There's also some more focused evaluation metrics, such as sentence scrambling, final sentence prediction, and final word prediction. And these are kind of targeted to find individual phenomena that require either understanding of discourse, so like unscrambling sentences requires you to be able to kind of model the coherence of a document. And these final sentence prediction and final word prediction methods, they essentially find individual phenomena in the entire document that seem like they should require context. And it becomes a more targeted evaluation. There's also a recently proposed composite benchmark containing several tasks, specifically the long-range arena, that is designed to test these document-level models. Okay, so now that we've talked a little bit about the mechanics of how we can do document-level modeling, I'd like to talk about a couple specific tasks that are kind of inherent to documents. So the first one is entity coreference. And so what entity coreference is it essentially is a two-step task of identifying phrases. For example, if we're talking about entity coreference, identifying phrases that talked about an entity. Notably, this is different from named entity recognition. So we might have Queen Elizabeth here, but we also have other phrases like her that are talking about an entity. And normally these would not be tagged in named entity recognition. And then the next thing that we want to do is we want to cluster these noun phrases referring to the same underlying entity. So basically we want to tell that Queen Elizabeth and her both refer to the same thing, and then husband, King George VI, the king, and his all refer to the same thing. So for noun phrase detection, this is actually quite tricky because if we look here, we have a renowned speech therapist and a renowned speech, and these are both noun phrases, but it's kind of hard to tell which one of these might be corresponding to another entity, particularly that we would want to be handling, detecting. And then you might also think of coreference as a clustering problem of given noun phrases, but detecting relevant noun phrases is a difficult and important step, and knowing the correct noun phrases affects the result a lot. So this shouldn't be overlooked as kind of a difficulty in coreference resolution. Traditionally, this has been done as a pre-processing step, but recently several models do this in kind of an end-to-end fashion. So we should also talk about the components of a coreference model. So like a traditional machine learning model, we need to know the instances that we would like to be classifying. We need to design the features that we use to classify the instances. And we need to optimize towards evaluation metrics. So I'll be talking about each of these kind of in turn. And also for coreference, we need a search algorithm for structure. And coreference is an interesting structured prediction problem because essentially it's a combinatorial optimization over all possible, assignments of noun phrases to clusters. So because of that, we need kind of algorithms that can handle this as well. So in coreference models, instances, as I said, the structure is a possible cluster structure is exponential of the number of mentions. And models are designed to approximate or explore the space of these partitions. And there's a number of different ways for constructing these models. They can either be entirely mention-based, so they can say that these two mentions belong to the same cluster, or they can be entity-based, which says, okay, we want to find the entities, and now we want to decide whether the mentions are belonging to each of the clusters. And this can be important because if we have Hillary Clinton, Clinton, she, and Bill Clinton, and we look at which mention to link to, Clinton obviously is a pretty reasonable choice for Bill Clinton being linked most of the time. And because of this, a model that looks purely at mentions might get a bit thrown off here. So that's an argument for kind of more sophisticated entity-based models. So if we look at mention pair models, the simplest one, basically what we do is we try to calculate the coreference relation between every two mentions. So we have a pairwise ranking model, or a pairwise model that tries to decide whether Queen Elizabeth and her are coreferent, Queen Elizabeth and husband are coreferent, etc., etc. And this is simple, which is nice, but it has many drawbacks. So it may result in conflicts in transitivity. So it might say that Queen Elizabeth and her are coreferent, and Queen Elizabeth and viable monarch are coreferent, but viable monarch and her are not coreferent. Another issue is that there's too many negative training instances. So they, most entity pairs will not be coreferent. So you get lots of negatives and you have an unbalanced learning problem. And perhaps most importantly, this doesn't capture entity or cluster level features like we would like to have for the Hillary Clinton example that I talked about before. And then there's also entity mention models, and entity mention models basically create an instance trying to classify which of the previous clusters in a next mention belongs to. So basically what you do is you step through, in order, maybe the natural discourse order, and try to decide whether the mention is coreferent with any previous entities. And based on this, you can create cluster level features like the ones I described on the right here. So there's a couple problems. One problem is there's no ranking between the antecedents. So, you're not necessarily able to, come up with a ranking of which antecedent a particular mention is likely to belong to. And also cluster level features are non-trivial to design, so you need to think of a way to do this. So one advantage of using neural network models for coreference is they allow you to learn the features with embeddings and allow you to easily train towards whatever metric you would like to be solving using reinforcement learning methods or margin-based methods like we've talked about in previous classes. And another advantage is that they've actually made it possible to jointly perform mention detection and clustering. So one kind of widely used model for neural network-based coreference, which has also been expanded since its original proposal in 2017, is allowing all features to be represented using typical neural networks, and also a neural network allowing errors to flow end-to-end all the way to mention detection. And this solves errors in mention detection causing downstream problems in coreference. So the way this model works basically is it's a model that has some sort of neural feature extractor. The original paper used an LSTM, but it could be, BERT or anything else that you would want. It could even be a long document transformer if you wanted it to be. And then what you do is you essentially take the left span, the right span, the vector from the left side of a span, the vector from the right side of the span, and have some sort of combination function between them. And then you concatenate the left side vector, the right side vector, and the combined vector, and feed all of them into a classifier that tries to predict whether the span is likely to be something that requires coreference or not. And so things like General Electric and the Postal Service are likely to require this, whereas surface contacted the is very unlikely to require this because it's not an appropriate span. So an important thing here is we get a mention score out of this. So then if we move on to the next to the next part, now we calculate a pairwise score. And the way it calculates a pairwise score is we have each of the individual mention scores added together with an antecedent score, which calculates the congruence between these two span representations. And these could be, fed through a multi-layer perceptron to calculate the score or something else. And once we've done this, if we have the company here, and we want to predict which of the spans is its antecedent, we now feed all of its antecedent scores, or all of its coreference scores, into a softmax and try to maximize the probability of the correct antecedent being selected. So one reason why this model is good is, or one very important thing about this model is now an end-to-end model, because the mention scores, which also have to do with mention detection, also get fed into this coreference score. So they also allow error to backprop into the mention detection score as well. So one other important thing that I forgot to put on the slides is this, calculating the pairwise scores over all spans in the document would be basically infeasible, because it would be, if we have all of the spans in the document are n squared, and then if we calculate all pairs of scores between them, that would be n to the fourth over a long document. And earlier in this video, I was talking about how infeasible even calculating quadratic scores over the entire document is, and that would be just completely out of the question. So this, another clever thing that this model does is it has pruning, where basically it uses the mention score to prune out spans that are very unlikely to be mentions that need coreference. And because of this, it allows for efficient calculation, essentially, all while training end-to-end. So yeah, this is a very nice model for coreference. There's lots of follow-up work. And one question that might be in the back of your mind is, why would we even need this kind of supervised coreference in the first place? And one reason why we would want to have this supervised coreference is for any sort of human-facing application where we basically want to identify who, for example, information extraction, who did what in a particular news article. Usually in a news article, you only mention the full entity name once, and then throughout the entire news article, you'll say like he or something like this. So if you wanted to basically allow people to search over news articles to find, what a particular political figure said or did, you would need to have these coreference relations to identify this accurately throughout your news corpus. Another reason why you might want to use coreference is for use in neural models. And there have been methods for example, coreference-aware language modeling that gradually build up representations of entities in documents, maybe across an entire book based on coreference relations. And also coreference-aware QA models that directly draw or upweight links between coreferent words in the sentence. And you might get some of this by end-to-end training, but unfortunately coreference relations, or the necessity to use coreference relations to perform good end-to-end QA is relatively rare. Examples where coreference is really important are relatively rare. So we might not expect the error signal that you would get from end-to-end models to necessarily upweight coreference enough. So this gives kind of an inductive bias to increase the model's interest in coreference. And we've also found some interesting things with respect to applying this in machine translation and other things as well. So the final thing that I'd like to talk about today is discourse parsing. So discourse parsing, basically what it is the parsing of an entire document with respect to the type of relations that occur between individual chunks of the document. And specifically, these chunks of the document are called elementary discourse units. And there are relations between them, like, for example, background. So we have, with its distance orbit, Mars experiences weather conditions. So we have a background that is used to basically explain why Mars experiences frigid weather conditions. And then we have an evidence relation between a long kind of elaboration about how cold Mars is or something like this. So we have evidence for Mars's experience of frigid weather conditions. So I think this is really interesting. Again, like let's say you want to examine kind of higher level information about texts, like their argumentation. If you have a particular fact that you would like to justify, or something like this, this could be a very strong tool. And there are methods for discourse parsing. One very interesting method that I have seen is this recursive model for discourse parsing, which basically creates a tree-structured model to build up the representations. I think you certainly could get something like this from a transformer model, but if you remember, transformer models are essentially doing attention over individual units in the sentence. And once we start getting up to higher level discourse structure, it's not necessarily obvious that the models would be able to be essentially, reasoning or calculating representations on the appropriate level of granularity to capture discourse structure. Another example of how you could implement something like this is with kind of attention-based hierarchical neural networks that calculate attention first over one individual words, and then gradually build it up to higher level representations using a hierarchical attention. So this would also be a good tool for something in this space. And finally, I'd like to point out uses of discourse structure in neural models. So discourse structured classification with neural models. I found this a very interesting paper because essentially what it does is it first calculates the discourse structure of long documents and then uses this discourse structure to provide an inductive bias upweighting the importance of particular discourse structures. So, for example, things like elaboration are less important than things like, the core argumentation, or how deep in the overall discourse structure you are. So this resulted in quite good results at the time. It's a paper from 2017, so a bit older. But one other interesting thing that I found in this particular paper is that the accuracy of the classification convincingly went up with the strength of the discourse parser. And because discourse parsing is still, relatively hard, it's kind of a harder, higher level task. I found this quite interesting. It kind of motivates more work on these harder understanding tasks for use in downstream applications. Okay, so that is all I have for today. And what I would like to talk about is, given the tasks that people are currently tackling for your projects, are there any examples of tasks that require reasoning over higher level structures or longer documents or things like this? And if so, which of the methods that I proposed here or I discussed here do you think are appropriate for that task? And which ones do you think are less appropriate for that task? Which kind of, intuitively, which ones do you think would work well for your task and which ones do you think would not work well? So for the people in the class, I'd like to discuss that in the discussion section. Okay, thank you very much, and that's all I have for today.